Hi, fellow geochemists and geochemistry enthusiasts. Welcome to GeochemiSTea, the only podcast for people who love geochemistry with a side of tea. Our mission is to inspire and to shed light on the topics not fancy enough to talk about at a conference, but important to delve into. I'm your host, Sam Scher, and this week we're meeting up with Pim van Geffen again because our bonus episode inspired him to delve into the topic further. Pim van Geffen is the technical director at CSA Global, working to illuminate the geochemical data of ore deposits. So Pim, welcome back to GeochemiSTea.
Thanks for having me, Sam. It's exciting to be back.
So for anyone that wants to know more about Pim's journey to being a geochemist, please check out episode 5 because we have a lot of ground to cover. And no offense, Pim, but I don't want to waste any time. However, we can't break protocol here, so since you're back for another episode, you got to pay the toll, and we need some tea, and you need to dish.
Right. Yes, tea. So, thought about this for a bit, and most of the real tea that I'd only divulge over maybe a beer at the bar, we'll have to just leave it where it is, I think. But one thing that did come up is I don't know if it's real. It's not so much gossip as an observation that I sort of see in our in a transitioning of our demographics. So, and this is not an age thing; it's more a thinking thing. Where in the past, I'm a fellow of the Society of Economic Geologists, and we just had the SEG meeting in Denver 2 weeks ago.
And I heard you got an award, so I want to congratulate you on your Pimminess award.
That was a very silly thing, yes. Well, maybe that's tea itself. That was a very silly thing. Maybe I should tell that story. Now that you bring it up. Yeah.
Continue on the track. Let's hear what you first
Okay, I'll go back. I'll go back to the track. Anyway, so for the past 10 years or so, ever since I started with David Lavi's group at IO Global, I've been sort of thinking about this geomet or ore body knowledge, or like how do we really cover more ground with what we can know about the mineral system early on, right? Like in mineral systems, not so much about how do they form only, but what happens when you find something, and what do you do with it, and what are other people going to do with it downstream? So the thing is that the last couple of SEG events that I've attended in person, especially pre-COVID, it was often sort of there was a dominance of people who would just have a pissing match about different ore deposit systems and different the actual deposit types and what to call a certain thing and whatnot, and there would be all these arguments about trivial stuff that was really not helpful in the space of what I like to think about as economic geology. Sure, it's all fundamental how these things form, and it's all interesting from an academic point of view. But when we're there discussing, economic geology, where is the economics? Where are you thinking about putting this into production, and what's going to happen next? And there's very, very little thought put into that usually, in the past, I should say. So this year, I was actually pleasantly surprised to see a lot more thinking, in the life cycle assessment, if you will, in all the external cost and considerations that come with the new hunt for critical metals, and we need to put the whole thing in context. You can't just have a a deposit, find a deposit, make a discovery, and then, count your ounces and tons and go. You have to consider everything else. You have to consider all the external costs. You have to consider all the closure costs. You have to consider all the community engagement costs and benefits. And you have to bring that all into your project. And I think more and more major companies are picking up on this, and they, so the more of this sort of risk assessment you do up front, the better your project's going to look, right? So of course the economics still need to be there in terms of mineral value to get it going, but you can't ignore all those external costs anymore. So I'm just excited that there's sort of a the zeitgeist, call it that. Like the people are picking up on this, companies are picking up on this, and the SEG is finally picking up on it too. That the discussion is shifting from a really narrow view of what economic geology should be to more of a, hey, we have a relevance in the world here. We have a societal relevance, and if we want to move to a green energy future, we need a lot more metals. How are we going to get those, and how are we going to, not just in the race for producing them, but how are we going to produce them responsibly? Just the other day we had a big tailings failure again. Well, this is diamond mine, but it doesn't. The point is we need to consider all these things, and they need to be done well, and we can do them well. So we should, we have that responsibility. Anyway, it's not really tea, but it's a little thing that I just wanted to share. I think it's close to my heart. Like I care about that stuff. I want all of us to do the right thing.
No, I think that does fall into the category of tea, because you're bringing up definitely something that you're passionate about, but something that's been, I think, wrong with not just the SEG, but other societies as well. And because for the past 5-6 years, I did a lot of conference touring, and I found that it was very hard for me to go and sit in on sessions because they were very one-dimensional. And it's good to hear now that SEG, at least for this conference, is starting to hopefully, make progress and go in the right direction, because I agree completely with you on that one. All right, well, I think that was some great tea. So don't undervalue yourself. But let's just jump right in. Okay, so typically our format here at GeochemiSTea is to talk about a paper with an overarching theme. Pim's case, book chapter, same thing, right? However, inspired by the bonus content from our prior episode, Pim came to me because he felt that this business was unfinished. Sam, he says, should we not do a separate session on analytical methods? It's really important that we only barely scratch the surface. He adds, we can keep it short. Pim, I'm in complete agreement here. This is such an important topic to talk about, and I don't believe in us to keep this short, though. However, I'm going to break this down into the important topics that I believe that we need to cover, so that hopefully we'll answer the vast majority of industry's questions, and we'll get them to think critically about important things to talk about with their labs about. Over the course of the next hour, we're going to focus on the importance of orientation surveys, prep, digest, finishes, and impacts on changing packages during a campaign. All right, you ready for this, Pim?
Oh, I'm ready. And I also rely a little bit on your audio editing skills to make it short later, maybe.
We'll see what we can do. Maybe it comes out in 4 different sessions. Who knows?
No. We don't want to bore our listeners.
Don't worry, audience. This will be fine. It will be fine. Okay, orientation surveys. The question I get all the time from geologists is, how do they know what lab package to choose? So for instance, especially if you're in a greenfields drill program, nobody seems to know. If you're doing a drill out, if you're doing soil, sediments, till, everything's very different. Everybody's a different experience. Times always change. What do you recommend when people come to you with a question like this?
Well, that's a very broad question. I mean, if you're going in green to a new area and you've never used, any of the methods available, or the methods available to you, or the methods that you understand are not applicable, then you have to come up with something else. And if you're really going into a new space with a new concept, then you need to run your orientation surveys, right? So we don't have to start every campaign with an orientation survey, because once we understand a certain sample medium and we understand certain, analytical technique that goes with that, and we have an established lab, we don't need to rerun every run the orientation survey every time. But I actually was talking with a client who was also a friend of mine and a former colleague, and he asked me about, I'm going into this swampy area, and there's nothing but swamp and trees. And, I wouldn't mind, seeing if we can sample the trees and do like a biogeochemistry survey. But like, where do we start? What should we do? What should we sample and what should we? Well, that's where you do an orientation survey, right? So this is where you really, hopefully you'll have some strong trend that you can already follow. You just want to sample, right? So you have some sense from geophysics or from existing operations nearby, or from structural controls on metal distributions. You have a site that maybe you haven't drilled yet, but you're pretty sure that there's something in the ground there, and just run a couple of orientation lines across your projected mineralization, and make sure they extend far enough into background so you can actually see the contrast. And then, take, I don't know, 30, 50, 100 samples, and then review those data before you proceed, right? To see that you make sure that you understand what's going on.
And when we say orientation survey, are we talking about, and I know we're going to get into this later, but I just want, so everybody's clear on this, what are we talking about exactly? Are we talking about just testing out the samples for what digester we use, for what finish, or are there other considerations that we want to take into account as well?
Well, sample spacing is one too, right? So you want to, depending on the size of the target you're looking for, you may have to sample quite densely. But what you want to avoid, this is in our old IO global training sessions too. What you want to avoid is sampling really densely over a target zone and then spacing out in the background. Because once you do that, now you get like the chance of hitting something in that dense area. It's pretty high. So, or you see some little spike, and you say, okay, well, look there, we did it right. So if you're doing, dense sampling, you need to extend that dense line all the way out into background. So it depends on the target. What are you trying to identify? What is the footprint that you expect a certain target to have at the surface if you're doing a surface orientation survey? So it's all those things. So it's sample spacing, the sample type, the what are you after in terms of elements? Because are you well enough aware of the possible pathfinders associated with your deposit types that you're looking for, to make sure you cover all that, and that you get so then you go to the lab and they say, okay, what kind of prep, what kind of analysis, what kind of finish, with digest. You have to piece all that together. So you can if you have done these kinds of things in the past, you can piece it together pretty well and just call up the lab, see what they offer, and but perhaps things have evolved since you last talked to them, or talk to a consultant and say, can you just help get me going, and at least make sure that we don't go off into the weeds.
I think you make a really great point by saying to talk to the lab, because everybody should know that all the laboratories out there, they have geochemists that are there to help you make decisions like this and give you recommendations.
Exactly. Yeah. So orientation study, it can be lots of things. So it really it's you have to put some thought into it before you even plan your orientation survey. You don't go just out there and sample a bunch of random stuff, send it to the lab, and that's your orientation survey, right?
Yeah, and if I could do a little bit of promoing for a different episode that I did, when I talked with Tom Carmichael about spatial autocorrelation, this is a really good follow-up to what Pim's talking about, of planning out your survey as well, and your sample spacings being quite regular, not really just clustered in a certain area, because then that also can lead to spurious results as well. Next section, talking about sample prep. When you first open a geochemistry lab schedule, there are likely going to be a whole slew of packages corresponding to how to crush and prep your samples. For example, crush to 70% less than 2 millimeters, rifle split off 1 kilogram, pulverize split to better than 85% passing 70 microns. What in general should a geoscientist concern themselves with in terms of crushing, splitting, and pulverizing?
Well, here is another whole episode on sample theory that you should do with someone else, because I'm not the expert there. But
I'll write that down.
In general, you would go, like, I don't know. So it depends again on your sample medium. But say we're sending half core to the lab, crushing, then splitting, and then the split then be pulverized to the digest specification. So there are sort of the standard procedures, and then there's the specific procedures for the special cases. In general, the important bit is that when you do a crush, like a comminution, so you go from one size to the next size. When you take a sub-split, you need to make sure that the material is fine enough to justify a representative split. Now, there is a beautiful graph that actually, that you can follow. I don't actually have it, but I've seen it presented. Where you see if you grind to a certain fineness, now you have so many grains in your sample, so now it's fine to split again. So every time you make it, if you reduce the grain size enough, that allows you to split again. So you just got to make sure that the splits that you take are not too coarse. So if you have a small sample and you crush that to a relatively coarse grind size, or crush size, then you're introducing noise and variance by splitting it. So you need to make sure that first step, if your sample is relatively small, that first step brings down the grain size far enough to justify another split. So you can get really into the nitty-gritty about this, but again, talk to the lab. They understand what they're doing, or they should, and it's usually a two-step process, unless you're really dealing with very specific issue. So if you have like texture issues, liberation issues, once you get into metallurgy, now it becomes really interesting, because if you get really fine-grained integrals of stuff, and but now rather than a sampling issue, it becomes an energy issue, right? So there's a sort of a diminishing returns once you get to the finer than 50 microns or so. If you get into the 20 and the 10 micron, then the cost, the energy cost of milling material that fine becomes prohibitive. So then, it's just not feasible for an operation. So I'm jumping into metallurgy here from exploration, but it's actually something to consider already when you do your work in the exploration space, to look a little further than just the grade, and then look into like, what's my distribution and what is the grain size, and do a little bit of variability test work early on.
Yeah, I have this conversation with many people about, even though that you're in the exploration phase, you should already be looking through to end of life of mine. So I think you bring up a really good point there. And my last question in terms of sample prep is that, as a follow-up, should a geologist be concerned about washing or cleaning the pulverizers or crushers? Is that something they should be talking to the lab about?
So here's the thing. We should not trick the lab. We should work with the lab. So sometimes we think we can just ship all our samples from a given project for the one method and just fill out one form and get it all shipped out. If you have high-grade samples mixed in with your soil samples, that's going to probably leave a trace, right, down. Because especially if you don't ask the lab to clean the crushing and grinding material in between. So it's really important that when you send a batch of samples, that it's like consistent sort of material, that there's no ore grade mixed in with background. And you should flag the high grade stuff. Some people, they don't flag massive sulfides going to the lab. Well, if the lab doesn't pick up on it when they open your bag, it can cause huge problems. To the point that things can ignite. They can self-ignite in these mills, because they get too hot, and then these sulfides just react and oxidize, and it's an occupational health issue. So it's really important to just be honest with your lab, tell them what's coming, make sure that your batch of samples is of relatively homogeneous material. If you do have a lot of high grade mixed in with lower grade, and you're concerned about that, and you can't split it up in batches, then just either like add your own blank right after and say, please process in sequence, right? Or ask them to wash after, after this sample, after that sample, or after every sample. If you have a lot of high or variable grade, to say, I want a quartz wash or whatever, after each of my samples, because otherwise you do get carryover. Yeah.
Yeah, no, and this is a great point just to underscore this of what Pim said, is that we're not in the business of trying to trick anybody or prove that, a certain method is better or not. This is about, getting results with tried and proven methods, and to give the best 43-101 that you can give. Like, this isn't about...
Get the most reliable results.
Exactly.
For your project, right?
Exactly. Yeah. Well said. Moving on now to digests. The common most digests that we use are aqua regia and 4-acid. So can you just go over quickly, what are they? What are the differences between the two? And really, is one better than the other?
So, better than the other. So if you're in a soil program, especially residual soils not residual soils, but like transported soils, or and you want to get like really low detection limits. So you don't want your entire sample to go into solution. You want to get that part that you're interested in solution. So then aqua regia, even though it's a strong acid, we covered this in our bonus episode last time, but I want to just mention it again, because aqua regia is a relatively strong acid, right? It's a mixture of hydrochloric and nitric acid, 3-to-1. And some labs have different ratios, but the traditional aqua regia is 3-to-1 hydrochloric to nitric. And the power in that is that nitric acid is a strong oxidizer, so we'll get your metals oxidized. But then to keep something like gold in solution, you need the ligands of the chloride to help you not let it precipitate again. So this combination of acids works to dissolve gold, and that's why it's called aqua regia, right? It's like the regal water, literally from Latin. So yes, it's a very robust. I mean, aqua regia varies from lab to lab, as I mentioned already. Digest times, digest temperatures, even acid ratios, acid to sample ratios, they all vary. So don't expect every lab to produce the same results from aqua regia digest. Same goes for acid, but let's stick with aqua regia for now. So the point is, if you're doing a soil survey, somewhere up in the Arctic, or I don't know, in transported overburden anywhere else, the aqua regia digest gets pretty much all your trace metals into solution. So as long as they're somewhat available, right? So the resisted silicates and oxides don't go into solution, but the metals of interest do. And it's the beauty of it is that you can actually then, if you then present it to a mass spectrometer, which we'll cover later, you can get these super low detection limits. And so this is for prospecting and regional exploration, and also stream sediments, for instance, really powerful stream sediments. Aqua regia, why not? You don't need to reconstitute the mineralogy of most stream sediments. What you're interested in is the dispersal of particular elements, and pick them up as well as you can with the lowest detection limits. So then aqua regia is a beautiful medium to use. As soon as you start drilling, though, or if you're working with residual soils in certain areas of the world, a 4-acid digest allows you to reconstitute mineralogy, because it dissolves much more of the sample, right? It dissolves most of it. So 4 acids, combination of hydrochloric, nitric, perchloric acid, and hydrofluoric acid. So the hydrofluoric acid comes earlier so a hydrofluoric acid is not a very strong acid from a chemical point of view. It's really dangerous, because if you get it on your skin, the molecules are so small, they penetrate your skin really easily, and they react with the calcium in your bones, which is not a good thing. So it's really painful if that happens. Well, we have a mutual friend, you can ask all about that, who's experienced this. So it's important that it's another occupational health hazard. but it's important to know that, to understand that step. The power of the hydrofluoric acid step, though, is that it breaks down silicate bonds, right? So it then reacts with the silicon to form silicon tetrafluoride, which is evaporated, and that allows everything else to go in solution. Now, we don't get the silicon number. We discussed that already. And there's a couple of other problems. So there's the perchloric step, which is, perchloric acid is also a bit of a danger matter material to work with. The MSDS is definitely something you want to consult before working with that. It can be quite explosive if it crystallizes, and it's a really strong oxidizer. So it's helpful to really break down these materials and get things into solution. But that said, if you have a very high potassium sample, you may form potassium perchlorate in that step, and you might actually lose some of that potassium in that process. So, this is again going back to this earlier statement of no one digest does it all. Another thing that happens is that, because it's so aggressive, there's also materials that evaporate and volatilize, right? So people are worried about, arsenic and antimony and a couple of other things that may actually volatilize in the process, which, can be a problem. Some labs have really figured this out, right? So they say, well, instead of drying our sample completely, which then actually makes it hard to get it back in solution again, we dry it till it's almost dry. This incipient dryness, as it's all buzz about for acid digest, and when you go to incipient dryness or full dryness, this incipient dryness allows this little droplet of material to still be liquid, and then if you take that up in your carrier acid, you can take it to the machine and trust that most of it will still be in there. Now, again, I mentioned before, some labs have spent a lot of time in this method development space and have figured it out. Don't expect your sample to come back again with the same numbers from different labs with that digest. Another important thing I think about the 4-acid digest is, it's a compromise, right? So we don't get the silicon and we don't get all the oxides, especially the high field strength oxides. So again, ideally, if you want to know everything that's in your sample, you have to go to a combination of methods.
Before we jump into that, because that's the next question, could you just define residual soil so that people have a better idea of when to use 4-acid?
Yeah, so residual soil is a soil that where the rock's been weathered, and eventually the soil profile has formed in this rock, but it is the rock that you're interested in. So it's not covered by a transported overburden that you're trying to see through. You're actually working with the material that is sort of the result, the product of this soil forming process. So it's and you can have like really deep weathering profiles in tropical soils or relatively shallow in higher latitudes. But the point is that if you're working with a soil that is a direct weathering product of the rock you're interested in, then you can just use a strong digest like a 4-acid digest to give you not only the trace element distribution, but also allows you to reconstitute some of the the mineralogy and i.e. rock types, so that you can actually use that to also build a geological map. One of the most published data sets actually is one by First Quantum Minerals in Zambia. The Trident soil data set it's been published, so we can talk about it. We can mention it here at least. I was really lucky that I happened to be in Zambia in 2012 when the data just came in hot off the lab, and we used it in a training session there for IOGAS. And the beauty of it is that if you do a 4-acid digest on these residual soils where you have less than 5% outcrop in the area. So it's really hard to find outcrop to actually map your lithology. If you use a 4-acid digest on these residual soils, you can map the lithology beautifully. And, Scott Halley's worked with the data later and is published on that. There's another group that did machine learning on it and it published similar results. Of course, if you have good data, it doesn't really matter what method you use to analyze it. You'll get those answers. And one of the things that we did just as a little exercise, I heard Mike Ridbred in your last session talk about, these RGB maps, and you can actually make an RGB grid map in IOGAS of anything, but, let's take potassium, uranium, and thorium and make an RGB grid map. So we have a red, green, blue color composite of the potassium, uranium, thorium data in the soil. And then we asked the geophysicist, like, hey, do you have an airborne radiometrics map? Sure enough. So they come with their map and we overlay it and it's 1-to-1 and it's beautiful. So it's really then, it corroborates and of course, when you get this cross-validation of the different methods, it's so much more powerful. And of course, then you can go and make RGB maps with principal component 1, 2, and 3 to actually just make your lithological map. Once you have that kind of data, where they had 30,000, I think 20 or 30,000 points, forget the exact dimensions, 300 by 300 meter grid. It's a huge regional survey, and I'm glad they allowed some publications on that because it's really it's really useful for everyone to see how that can be used.
Excellent. I loved that little tangent.
Little rabbit hole.
I love it. But getting back to it though, and building on one of your last statements before I made you go on that residual soil tangent, we hear a lot about lithium metaborate fusion and that it's, the strongest digest out there. When we hear strongest, I think a lot of times we associate that with giving us the best results. Could you make a comment on that?
Well, so this is where my expertise, like I mean, there's lab experts who can delve deeper into this. But the beauty of the lithium metaborate method is that it's really a flux, and it's another method to break down the silica bonds, get everything into solution. But before you get into the solution, you actually first fuse it into a glass bead, right? So you make this fusion with this lithium metaborate salt. So you add salt to your sample, right? And you then fuse it all, and then you expose it to the digest to bring it into solution. Now, there's some assumptions involved there. I just had a recent interesting chat with a guy from SGS who they've done some work on looking at these beads that come out, and if you have things like high bromine, the bromine can actually coat sort of on the outside, as so it doesn't actually homogeneously disperse throughout the bead. So there's some issues with the method there in terms of getting everything into solution. But getting back to detection limits, we have to sort of talk about digest already too. Yeah. So I mean, not digest, but I mean finishes. So we go from digest to finish. To get low detection limits, you need to have low total dissolved solids. So if you add salt to your sample and then fuse it and then bring the whole thing into solution, you get a pretty thick solution, quote unquote, right? So what happens is that your detection limits are not very good when you have these really salty solutions. So you then have to dilute. And if you dilute far enough, then you also lose your signal. So it's a bit of a compromise again. So this is why when you do a whole rock characterization, you use the fusion to get your major elements and some of the more abundant trace elements into solution and get those analyzed. So you get your silica data, you get all the major elements analyzed, right? But then for your trace elements, you may still have to use some other methods that are less salty, have lower TDS. To get to get the element of interest, the analyte, to a low enough concentration.
Yeah, and then this is, just speaking to the audience, this is why you see in your lab schedules that you have these whole rock packages that aren't just one method, they're a combination of multiple methods.
Exactly. Yeah.
Yeah. And then moving over to gold, I'd like to just talk really briefly about fire assay. Can you just describe this for us?
Just, yeah, it was a really simple process.
Super simple. I know you got this.
Well, I guess I should have read up on the details a little bit again, but so I'll have to dig it up for my memory. But essentially, what we do is we take our sample, we put it with a flux and some lead oxide into crucible, and we heat it all up. So we fuse that, and then what happens next is that we pour that into a to let it cool off, and the lead will actually then settle out of our fused bead, and it'll collect all the precious metals. Right. So what happens next is that we take that lead button, and we put it on a cupel, we call it. These are, so the exact material composition of the cupel I don't have, but the point is, like, we take this lead button, we assume that all the precious metals are in the lead button, we put that back into the oven, and what happens next is that the lead is then oxidized now and sucked into the cupel, and the precious metals are left behind in a prill. So that prill that we then analyze for precious metal content. Sometimes we add a little silver or something to just make sure that we have enough of a prill left at the end if our precious metal contents are pretty low. But that's sort of the process. So there's several steps involved, and then there's screen metallic fire assay, which is a separate story. This is for coarse gold, where you actually after your crushing step, you make splits of fine and coarse, and then you analyze both of the coarse and the fine by fire assay. And the reason you would do that is if you have coarse gold and you would grind it all very fine, the problem is that some of the gold can actually smear onto your grinding equipment, and then and you may lose some of that. So so sometimes if you have coarse gold, then screen metallic fire assay is required. So yeah, it's really a 3-step process, right? So it's this original fusion under reducing conditions that goes, your litharge goes from lead oxide to lead, and in the process then collects all the metals. And then once you've got that lead button and you extract all the lead from it under oxidizing conditions, then you're left with your precious metals. So Linda Bloom actually has a beautiful exercise on this, where she goes through all the things that could go wrong in the process. And the final conclusion, I can give this away here, I think. It's another bit of tea. Maybe she'll beat me over the head. But the final conclusion is that in the process, there's so many things that can go wrong. Most of those things end up in you losing gold. So generally, your fire assay is sort of a minimum, amount of gold that there's there. Like it's hard to get overestimations, unless there's poor calibrations, to get an overestimation of your gold content. So in the process, there's all kinds of things that can go wrong. If you don't have a total fuse, and perhaps some of the metal is still scattered in your glass bead, and you lose that, right? So if it doesn't all collect into the lead button, then again you lose metals. If it splatters because there's some reactive material and you don't see that, and or it splatters from one crucible to the next, there's lots of things that could go wrong. So it's actually surprising how well this technique has been established, and what a great job the labs are doing in this space to get reliable, reproducible results. So yeah, it's quite involved. Read up on it. Go check if I explained it correctly or not.
I was gonna say, for somebody that didn't remember, you sure, went in deep, even as much as to give away Linda's secret. So hopefully you don't get in trouble for that.
Well, I didn't give away all the secrets. Just the
Nice.
I just sort of the spoiler was there.
Okay.
So maybe you should be a spoiler alert at the beginning of the session.
I'll try. I'll see if that's like a thing. And one last thing, and probably your answer could just be, simple that just talk to the lab about it. But in looking through a lot of the different schedules for all the major labs, one of the things that you'll notice is that they have a lot of different cyanide leach packages that vary in cost for the fire assay. And I was just wondering if you could just comment towards, is the most basic package good enough, or is it better to every time pay for the most expensive package? Or is there something that people will lose by just assuming that, we don't want to pay all this money, we're just okay by doing the least expensive package?
Well, okay. So again, we didn't talk about the finish of the gold fire assay, because once you have that prill, now there's two avenues you can go down. You can do a gravimetric finish, which just measures the mass of the prill, right, with the microbalance, or you can dissolve your prill and then measure the content, in solution. So that final finish, actually, gravimetric is not so common anymore. But if you have really high-grade gold, then gravimetric is actually fine. The balances are good enough to do that. And yeah, so if you have enough of a prill, enough substance, then the precision on that is pretty good too. But if you're working with really tiny prills, especially if you had to use like things like silver to bring, to help make enough prill, then you really need to dissolve it. You mentioned cyanide digest, which is a bit of another story again, where we talk about, now you're talking about leachable gold, bulk leach extractable gold. Blag is one of those things. This goes back to not the fire assay, but the like soil digests or metallurgical work in the space of leach pads and those kinds of things. Now you're talking, pull up another can of worms.
We're talking about
what
Blag
goes
next.
into solution, right? And
yeah,
Blag, yeah, it's beautiful if you have low concentrations of gold, well dispersed. If you have really nuggety gold, it can actually not get everything into solution. It'll dissolve some of your nugget, but not the whole thing. So depending on the leach strength and cyanide content, the bottom, the temperature, the length of the roll, anyway. So all these factors factor into that again. But generally, Blag does a great job at finely dispersed gold to collect it all. But yeah, high nuggets, it can be problematic. So especially goes again to the metallurgical space, right? So if we're just dealing with soils, then we're generally in fine terrain because we don't expect big nuggets in our soil. However, stream sediments, of course, are a bit on the edge, right? So if you are specifically looking for gold and you know that you're in a district where you expect maybe coarse gold, then maybe run your screen fire assay, or no, not screen, or the fire assay instead of the Blag. But the Blag is still, again, people say it's for regional, even for these regional surveys, even if you have really coarse gold in yours, the Blag will still pick up a signal, right? So maybe I should rephrase that statement about stream sediments. Blag should just work fine there still. If you want total gold content, you have to be aware of the coarseness of your gold.
All right. So I guess then we could skip the next question because it looks like we just covered it. I love it. For my next question, I had wanted to ask whether the digests used are standard between labs, but I think you did a really good job of talking about that when we were talking about aquaresia and 4 acids. So with that, I'm just going to move on to my last question about digests, which is that if you look at any schedule, there are a lot of digests. So you have different ammonium acetates, hot, cold, you have MMI, et cetera, et cetera. And the question that I have for you in this one is that there's a lot of thought behind that. Using different leaches, you're always going to definitely see anomalies, and it's really going to help you in this specific type of terrain. And I What I just want you to just expand upon a little bit is just maybe just simply, what are your thoughts about using other leaches? And is it something that is simple, or is it a bit more complicated?
It's quite complicated, and this was part of my PhD thesis actually, which looking at all these different digests for a particular set of soils. And the end conclusion was like some of the weaker digests still work, but in my case, they wouldn't work better than, say, an acrid digest on the clay fraction of those soils, right? So in that case, what I found that you get these clay organic complexes in humic soils, where this is where the metals reside. And if you understand your soils well enough, whether your metals of interest reside in oxides, iron oxide, manganese oxides, or if they reside in organics or in clays, or a combination of organics and clays, which was the case with my work. Yes, you can then design a leach that picks that up. Like, for instance, the sodium pyrophosphate leach, which is kind of a soapy leach at high pH 10. It's kind of an odd one out there. That sort of breaks down your organics and then brings things into solution that are adsorbed to those organics. So, but yeah, that sort of gave me similar results to Acarrhisia digest on the clays, because that clay fraction was where that fine fraction was where the organic clay interplay was really sorbing all the metals. So I think, yeah, we could have another whole session on the weak digest, but I kind of want to, if you read up on the very weak digest, where they look for a transient signal that you would not pick up in the stronger acid digest, I have not heard of a deposit that was found by just using that in isolation. So usually it's used in combination with other methods to corroborate what's going on, to cross-validate, and then you might as well say, go with the more robust one, but it's also cheaper. So, I don't want to give too strong an opinion otherwise, but I think what's really important also is that we go a little bit into the finishes and stuff, because we only have a couple of minutes left. Of course, you can edit this down, but yeah, the finishes is where a lot of people have no idea what's happening.
That's a really great transition. For everybody out there, the most common finishes that we hear about are a regular ICP, OES, AES, MS. Are these the same, or are they similar enough that we can use them interchangeably?
Good question. Yes. So generally, when people say ICP, they mean, but they don't know that they mean ICP emission spectrometry. And some people, in some machines, that's branded as optical emission spectroscopy. Others, it's branded as atomic emission spectroscopy. So ICP, OES, AES, and ES, or ICP by itself, they're essentially all the same thing, right? So you should read up on the principles. The nice thing about it is that that you can put really high salty solutions, so high total dissolved solids, TDS solutions in that machine, and as long as the salts don't precipitate on your nebulizer, then you can actually really feed it thick solutions, because you're not feeding it into a mass spectrometer. You're looking at the emission spectroscopy. So in the plasma, you get these atomic emissions or optical emission spectra, because it's not just atomic. Also, some compounds also have their own emission lines. That's why the more correct term would be OES, which is optical emission spectroscopy. And you just look at the emissions of those lines, and you measure the spectrum. And from that, you can then calculate the contents of each element in your solution. Now, the problem with that is that, of course, when you have really high salty solutions, you do get some interference and overlap of peaks. But the thing there is that the detection limits are just a bit higher than you could get with a mass spectrometer. So let's go to ICP-MS. Usually it's specified if you do ICP-MS, because you also pay a little bit more. MS stands for mass spectrometer, right? So ICP we didn't specify yet, but that's inductively coupled plasma. And inductively coupled plasma is, we take a solution, we aspirate it, then we nebulize it. It goes into this plasma where it's then quickly evaporated and then ionized, first atomized and then ionized, right? So, and these ions are, what give off the emission spectrum, but these ions are also the thing that we shoot into mass spectrometer if we have one. Now, the mass spectrometer, by the time, you're operating in pretty low vacuum, so the actual stream of particles, by the time it reaches the mass spectrometer, is like 1 or 2% of what you feed it. So it's a really small fraction. The nice thing is, though, that you actually essentially measure individual particles hitting that mass spectrometer. So you can go down to very, very, very low detection limits in your solutions. But this is why we talked about total dissolved solids earlier. If you have too much, it can actually overwhelm the detector and break it. So if you have too salty solution, this is why you can't go too high on the TDS. You have to have pretty dilute solutions to feed into mass spectrometer. And that's why if you use an Aquaregia digest, you just get the elements of interest into solution and not all the silicate goo, And then you get beautiful results for your for tellurium and bismuth and arsenic and antimony, any of the trace elements for gold or other styles of mineralization. You look for these traces. Also, if you want to do any kind of lithogeochemical work with trace level niobium, titanium, zirconium, you get those all to really good detection limits.
And then in terms of other finishes, the last one that I really was thinking about, but we really covered very well, was fire assay, AAS, AA, gravimetric. Is there any other comments that you want to make that we haven't yet covered?
So the AA is the atomic absorption spectroscopy, AAS full on. It's an older technique, but it's a reliable one. The problem with that one is that you can only measure one element at a time. So you can have different lamps. Say you can have a revolver with up to 8 lamps cycling through. That measures 8 different elements, but that's sort of the limit. The neat thing is with gold, once you've concentrated it into that prill after your fire assay and you dissolve it in an Aquaregia solution and you then feed it to an AA, you just get your gold number from that, and that's much higher concentration than was ever in your sample because you pre-concentrated it. So you're not too worried about the detection limit issues with AA otherwise, right? So if you do just a straight up soil digestion, then you're working with pretty high detection limits plus a really limited element suite. So yes, AA definitely has its purpose in mine labs, in fire assay finishes. People are using ICP ES as well, right? OES, AES, whatever you want to call it, for gold post fire assay, and that's fine. So it depends. If your grades are high enough, then the AA is totally capable of giving you good numbers. So ICP we covered, AA we covered. Another thing, I think you were going to ask it, but you haven't yet. Talk about XRF, right?
Perfect.
So XRF.
Now you're asking the questions as well.
Beast. I was prepared. I told you this time. A little bit at least. XRF, a lab-based XRF, is a wavelength dispersive XRF. It has better detection limits than a handheld energy dispersive machine. And it generally works with fused beads. So again, you get all your elements in that fused beads. Now, as long as that fusion's gone well and everything is equally distributed, you can actually get really good numbers on that fused bead because you remove some of the mineral matrix interferences. Of course, the metal interferences still exist, but you can get pretty reliable data, but it requires a really big lab-based machine. In the field with your handheld, you're dealing with an EDS spectrum. EDS is energy dispersive spectrum, which is which is more fraught with interferences and precision issues. So there's a limit to what you can do with that spectrum to actually tease out the trace elements, right? So things get overwhelmed regularly. So it's so important to do QA/QC there. And the other thing to keep in mind, I think the important bit about XRF is that it can only measure things that are like heavier in periodic table than fluorine, right? So even sodium and magnesium are pretty light, and you can't really get those on a handheld XRF. Even though, if you have very high magnesium concentrations, you can get reasonable numbers, but it's hit and miss. So to actually get decent detection limits for sodium, magnesium, and silicon, even aluminum and silicon, which are kind of important. The technique is a bit limited. So, but the lab-based one, it gives reliable results. It does not give the low detection limits of a mass spectrometer. But for the major elements, you get most of it. Again, sodium, you may not get all the sodium. I mean, in terms of getting a reliable detection limits, and that's just it depends a little bit on the system. But if you operate under a vacuum, you can go lighter, right? But you're sort of pushing the limits the closer you inch towards oxygen there.
Yeah, no, I love that you took the initiative here to talk about also the difference between the PXRF versus the lab-based XRF. A+.
Fundamental differences. But again, fit for purpose. If if you can make it work for your program, and if you do your QA/QC, there was a recent thread on LinkedIn asking about that. And as long as you do proper quality control, you can do a lot of interesting stuff with those machines. But it's not a lab replacement yet, and likely to go there because we're pushing the limits already with the current machines. They're really powerful. They're really, actually incredible machines for what they are, but I don't think they're going to. There's little room in the physics to get better than they are now.
We're coming to the wire here, but I think it's important to just push on and finish this out. So I have some combination digest finish questions. The first one being, what is the difference between collecting 4-asset data for aluminum, magnesium, calcium, etc., and collecting a whole rock analysis with XRF and ICP for the major rock forming elements?
Yeah, so this comes down to the sort of the fast compromise. So if you in your orientation survey figure out that you can get away with a 4-asset digest, that you don't need the whole rock full characterization every time, then go ahead and do it, because it's a lot cheaper to just use the one method. But if you need accurate and precise results for all those elements and your traces, now a whole rock or a full characterization package may be helpful. And some labs have again focused on that, on really sort of perfecting the fusion and then a combination of ICP, ES, and MS. So they would run the major element oxides on the ES, the emission spectrometer, and only the trace elements of interest on the mass spectrometer. So it's really a combination of this different package of these different analytical processes that give you that package. So there's real value in it, but it is a cost consideration. But I'm just going back to my little mantra is, if you have a budget if you start drilling and you have a budget for 10 holes, just drill 9 and get your whole rock package. Do everything, do even some basic mineralogy and perhaps some variability test work. So that you already cover that. Some environmental work perhaps also. Anyway, so the cost of running a drill program in total to get that sample is going to completely overwhelm the cost of the sample, the analysis. So if you sit there and just look at the schedule of rates of a lab and say, oh well, I'm going to pay 5 times more for the whole rock, package. I don't know if I want to do that. Like, it's 5 times my analytical budget, but it's not 5 times the cost the value that you get out of it is so much more. And it's so much more important to establish that early on, because it's going to be way more costly down the road if you have to reanalyze 1,000 holes, right? So
Amen.
make sure that you do that early on, invest a little bit, and for the cost of one hole, you can get, the other 9 analyzed to the T, and now you fully understand the materials you're working with, and you can then decide to dumb it down and work with, perhaps a 4 acid digest. Maybe that's it. I've worked on a project where this was a polymetallic deposit, and they said, well, yeah, the 4 acid doesn't really give us the detection limits we like. So we were using a combination of acarija and 4 acid. That also happens. Just use those, and then you get a deal on that with the lab. Talk to your lab what's best, and if you then don't know, then talk to a geochemist outside of a lab, like one of us. Sam
yeah, one of us.
Now.
Yeah, exactly, exactly. And if I don't know things, I got tons of friends where I'm just like, hey, Pim, What do you think about this? That's the benefit you get with the geochemist. It's not just one of us, you get all of us.
Right. Pretty much.
What is LOI, and why may it be important to collect this data?
Yeah, LOI is loss on ignition. So it actually measures the mass loss of your sample when you heat it up to, say, 1,000 degrees. So when you do that, you can imagine that things like crystal water and also carbonate and some sulfide may actually then leave your sample. And generally, it's actually used as a proxy for volatile content, essentially, but mostly for water. So in non-carbonate samples, it can be used as a proxy for water. Sometimes in carbonate samples, it can actually be used as a proxy for carbonate. Depends a little bit, again, orientation survey. But LOI can be really useful to also give you an idea, if you're working in, say, a porphyry system, the degree of hydrothermal alteration. How much water has your rock been exposed to? So it can help in that sense too. So to give you, and it gives you sort of the balance. So if you do a whole rock characterization, you get all these the metals in the solution. But what about your water? You haven't measured your water yet. So it's just to round that out. And you can, of course, if you have sulfur and carbon data as well, you can correct for the carbon that, if you know the speciation of your carbon, you can correct the LOI numbers to actually come up with the water number, how much water was in your sample. So yeah, that's total water, right? So including crystal water. So yeah, LOI, it's useful measure to add onto your package, especially if you have 4 acid digest, because it also then helps you to again, if you don't have too much carbonate, to back calculate maybe your silica data.
And another question that we have is, there's a lot of ways to analyze sulfur and carbon. And can you explain to our listeners about why you would choose sulfate or sulfide when you could just get total sulfur, or carbonate, non-carbonate carbon instead of total carbon?
Yeah, well, the sulfur sulfate is that's actually an interesting one. This goes back to metallurgy. I did work on a project where there was an issue with lead and zinc. The total grades looked pretty good, but then when you looked at the actual recoverable lead, it wasn't that great. So what was going on? Well, if you only have 4 acid digest, then you see lead and sulfur, and you can make a plot of lead and sulfur, which tells you how much galena there is, right? In the lead sulfur ratio of 1 to 1 in terms of molar ratios. So the problem there was that there's a mineral called a secondary mineral called anglicite that is lead sulfate, which actually has the same lead sulfur ratio. So you wouldn't see it in your total digest or in your 4 acid digest. So you need to know your sulfur speciation, right? So that's when you then go and look, okay, how much sulfate sulfur do I have? And once I've accounted for things like, hopefully there's not too much else going on in terms of jarosite and gypsum and all these other wonderful minerals, to help you understand how much of your lead is in sulfate versus sulfide. Because this makes a big difference. One is just not recoverable in a flotation setting. That's one example. Carbon, again, fit for purpose. Why would you use carbon speciation? Well, in some cases, you may have problems with organic carbon in your gold heap leach, because what happens is that some of the gold that's mobilized is then actually trapped by carbon. So we call that preg robbing, right? So then it's important to know how much organic carbon you have in your system. And if all your carbon is just in carbonates, then it doesn't matter so much. So, but you need to know the difference. So a total carbon number wouldn't give you the same sense of how much of each is present. So again, it really depends on your particular purpose, whether you need it, whether you need carbon data to begin with. But, and this is where I want to make a bit of a pitch, when we talk about life cycle assessment, you should actually get your carbonate numbers, or at least total carbon, just to also assess your environmental parameters. Because now, if you have that already, top to bottom of your core, it's a small add-on in terms of cost. It's a couple of bucks on a sample, but it then allows you to really accurately predict acid rock drainage, acid and metalliferous drainage, from your data. So it just in that neutralization potential, you're dealing with sulfur and carbon. And if you have, so again, do the speciation on your first 9 holes, right? And once you figure out what species you're dealing with, you can probably get away with the total number, right? So, and if you get good sulfur data on your ICP numbers, and they're good enough, fit for purpose, then you only have to add on carbon.
Well said. Thank you.
Just some ideas. This is not the complete story. We don't have
we don't have time for complete stories. Our wrap-up questions. I have 2 wrap-up questions for you, and I think that our listeners will love them. The first one is a database question. So, for instance, let's say that you receive a database and it has 16 different copper numbers, and then there's one column that says copper_best, which has all of these copper numbers. What does necessarily, I know it might be called different things, but could you explain the idea behind giving one column of copper numbers only, and if that's useful for plotting in 3D for doing further analysis, or if for each sample we should be looking at individual copper numbers? Same with gold and any other element.
Well, if I would get that kind of a database, I'd be quite happy as long as those 16 columns are preserved. What usually happens is you get a database and the best may still be there, but it may also not be there, and you may not be aware of that. And then once you start doing your EDA, you find out this looks a bit funny. Things look to be controlled by area or per drill hole, or what happened. Different methods, but don't worry about it. So for copper, it's usually not that big of a deal, because most techniques that we've discussed so far actually work just fine with copper. So, but still, if you have those 16 columns, look at what the protocol was to decide which, to rank and prioritize each number, and make sure that that's done sensibly, and then also look at the effect of each method. So just make your probability plots and do your comparisons between the different methods to make sure that they're comparable, that you can indeed sweep them together into one bucket. With gold, this is a much bigger issue actually, where you can have Acarigea gold, you can have black gold, you can have fire assay gold, all these different gold numbers, and if you sweep those all into one column, especially without letting anyone know that you did that, you get in real trouble, because the fundamental differences that we have discussed earlier in the episode are so great. So it's really important to keep track of the original methods. And sometimes you can merge them to just straight up. Sometimes you can apply a leveling to then at least work with them together. And sometimes the different methods are so fundamentally different, like for instance, weak acid digest or the very weak leaches with Acarigea or strong acid digest or fusion, they're not comparable. And then you just have to treat them separately. So you can only look at them in isolation. Again, quality control, critical. But yeah, so it does require a review whether it is appropriate to merge and call one column best. At the same time, it is good practice to do it. It's really useful if you can sweep all your copper data into one column, as long as you've checked the box that it's appropriate, then it's very useful to have that one column and work with it, right? That's again fit for purpose.
Great. And my last question, which I just think is so fundamentally important to comment on, and I think it would be irresponsible if we didn't mention it here, is what are the impacts, if any, on changing digests, finishes, labs, soil fractions, etc., in a single project?
Well, hopefully through our two and a half episodes now, we've covered that. So yes, changing sample media, absolute. That's a fundamental shift. That's a big difference. Yeah, so you're going to have to look at your data separately now, right? You can't mix soil and biogeochem data or stream sediments and soils, or they're fundamentally different things. They're fundamentally different samples. So yeah, you can't really mix those. Of course, you can mix the end products once you've made a map, and then you can overlay them and you can do all your GIS post-process, but you can't really mix your data. So that's just there's some real problems there. But yeah, the more subtle thing is switching lab. Switching lab is a big decision. And even though, your new lab may reproduce your copper and gold numbers quite well, if the rest of the analytical suite is so different that you can no longer really compare your trace elements of interest, for maybe, say, reconstitute mineralogy, rock composition, do this kind of lithogeochemistry, it can be quite different. So, you must have a real problem with your current lab to switch. If there's any way to just get to the bottom of the issue and work with the lab to fix it, then stick with your lab at least throughout that one project. I would generally advise, if you have the means, against switching labs within a project. So last resort.
Last resort. And then, I mean, I was on a project most recently. They changed, I don't know why I couldn't figure it out sooner, but it ended up taking me a little bit. But they had been alternating 4-acid with acarija downhole wherever they saw that they had a high grade copper zone. They were doing 4-acid. Once they didn't see obvious mineralization, they were doing acarija. Again, I'm embarrassed to say it took way too long for me to figure it out, but that was something as well that was just...
It's one expensive way of creating a lot of useless data.
Right. It was so sad. Yeah. Anyway,
yeah,
it was fun to have
that's just a waste of money. That's a big waste of money. And time and effort on everyone's behalf. Yeah, yes. Don't do that.
Don't do that, guys.
Sure. Yeah, I mean, do the one method everywhere and then complement if you have to. But I don't know. We talked about this before. If you want to do anything with your rock composition, which you should be interested in from a life cycle assessment point of view, 4-acid or whole rock, just go as soon as you start drilling.
Yeah. Don't make me sad. Don't do it to me again. Don't break my heart.
Everybody out there.
Everybody. Don't break
anybody's heart. Find me on LinkedIn and harass me if you disagree. But I'm happy to have these discussions with anyone.
I love it. Everybody, thank you for listening to this month's GeoChemiSTea, and a really big thanks to Pim for coming back, dishing some more tea, and taking us on this analytical method journey. Thanks to our sponsor, LK Consulting, and to It's Water and Coma Media for our music. And I look forward to chatting with everybody next month. Till then, enjoy all the geochemistry that you guys have at site.
Thank you, Sam.
All right, bye.
I'll talk to you.
Yeah, always.